Show by using the principle of mathematical induction that for all n belonging to the set of natural number, this equation is true. Meaning, we don't have to prove this equation, but what we have to do is we have to show that this equation holds true for any natural number that we choose for n. Okay, and it's given here the values of a1, a2, and an plus 1, with the condition being n is going to be greater than or equals to 0, a is greater than 0, and uppercase A, that's also greater than 0. That means these are positive numbers. Okay, let us begin. Now, since this is a problem related to mathematical induction, so we'll have to consider a statement. So let us suppose let P of n be the statement. P of n be the statement. We have the statement P of n such that we have an minus square root of a whole divided by an added to square root of a. So this is going to be equals to a1 minus square root of a whole divided by a1 added to square root of a. Square root of a. So this is going to be raised to the power of 2 whole raised to the power of n minus 1. So let's label this as statement number 1. We need to verify that this is a true statement for all n belonging to the set of natural number. First thing first, so let's verify that this is indeed a true statement. So what we'll do, we're going to consider the natural number 1. So for n equals to 1, we'll have the statement P of 1 such that we have a1 minus square root of a. So here we're replacing n with 1. This is going to be divided by a1 plus square root of a. This is going to be equals to a1 minus square root of a whole divided by a1 plus square root of a. a1 plus square root of a whole raised to the power of 2 raised to the power of 1 minus 1. So that's simply 0. So 2 raised to the power of 0, we know that's equals to 1. So here clearly we observe that the left hand side equals to the right hand side. So this tells us that the statement P of 1 is a true statement. Fine. So we have verified that the statement P of n is true if we choose n to be equals to 1. So we'll have to check if it is true for other natural numbers as well. So here what we'll do, we are going to make an assumption. We will suppose that let n equals to m. We're going to consider another natural number m such that P of n is a true statement. So we're supposing that P of m is true. Now what is P of m? So here P of m, this is the statement. We can take the help of the statement P of n, and wherever we see n, we can replace it with m. So we have am minus square root of a whole divided by am added to square root of a. Fine. So this is going to be equals to, we have a1 minus square root of a whole divided by a1 added to square root of a. This is going to be raised to the power of 2 whole raised to the power of m minus 1. So let's say this is statement number 2. We are assuming P of m to be a true statement. And using the statement P of m, our goal will be to verify. Our goal will be to verify that the statement P of m plus 1, we have to verify that this statement is also true. This is also a true statement, and m plus 1, this corresponds to the natural number consecutive to m. Okay, so what is P of m plus 1? First, let's write it down. So P of m plus 1, we can take the help of the statement number 2 to write P of m plus 1. So here we have a m plus 1 minus square root of a whole divided by a m plus 1 added to square root of a. This is going to be equals to a1 minus square root of a whole divided by a1 added to square root of a whole raised to the power of 2. Now in place of m, if we replace it with m plus 1, So we have m plus 1 minus 1. So this is what we have to verify. So let's call it number 3. So our goal will be to verify that if p of m, statement number 2, is a true statement, then p of m plus 1 must be true as well. Okay, so we will take the help of 2, and there are also some given values. So let's note those given values as well. So here we are given the value of e1, we are given the value of e2, and we are given the value of an plus 1. So let's note these values. So in order to prove statement number 3, we'll start from the left hand side of the expression. So here we have the left hand side, which is given by, we have a with index m plus 1 minus square root of a whole divided by a m plus 1 added to square root of a. Okay, now we are being provided with a of n plus 1, which is half multiplied to an plus a over an. So here what we'll do, in place of a of an plus 1, we'll take the help of this formula and replace wherever we see n with with m, such that we get in the numerator half multiplied to am added to a over am minus square root of a. And then in the denominator, what we have is half multiplied to am added to a over am added to square root of a. Okay, now let's further simplify by multiplying both numerator and the denominator with 2. So that's going to give us 2 and as well as am. So we get am squared. Let me write it down. We're going to multiply the entire numerator with 2 times am. Similarly, we're going to do that to the denominator as well. We're going to multiply with 2 times am. So that is now going to give us am squared added to, so we have a minus 2 times am times square root of a. Then in the denominator, we're going to get, we have am squared added to a added to 2 times am times square root of a. Fine. Okay, now we will simplify the numerator and the denominator. We have to rewrite the terms first. Now am squared, that can be expressed as am whole squared. Then we have a, so a can be also expressed as square root of a whole squared, means exactly the same thing, minus 2 times am multiplied to square root of a whole divided by, we have am squared added to a, so a can be also expressed as square root of a whole squared plus 2 times am multiplied to square root of a. The reason why we are rewriting the terms in both the numerator and the denominator, because the numerator can be expressed as am minus square root of a whole squared. This means exactly the same thing. The expanded form is the numerator in the previous step, and the denominator can be simplified to get am added to square root of a whole squared. Fine. Furthermore, what we can do, we can use some laws of exponents to rewrite the expression as am minus square root of a divided by am added to square root of a, and we can raise it to the power of 2. However, we can also write 2 as 1. It will mean exactly the same thing without making any difference. But the reason why we're writing in this particular fashion, because now we are going to make a change here. So here we're going to replace m with 1 and we're going to replace 1 with m, such that we get a1 minus square root of a whole divided by a1 plus square root of a whole raised to the power of 2 raised to the power of, in place of 1, we're going to write it as m. And we are almost done. So now we have a1 minus square root of a divided by a1 plus square root of a whole raised to the power of we have 2 raised to the power of m, but we can rewrite m as m plus 1 minus 1, and it means exactly the same thing. The reason why we were making this transformation m going to 1, because m is the index. Now m stands for the index, so here in our case the m is taking the value 1. Fine. And what is this? This is exactly the expression on the right hand side, and this is what we wanted to show. Let's check with statement number 3. Yes, this is exactly what we wanted to show. So what we have done here is we have showed here that the left hand side of the expression equals the right hand side. If this is the case, then we can say that the statement that we considered, p of m plus 1, so this is true. This is true. So what we have done here is, thus we considered the statement first that p of m, this is a true statement, and with the help of this statement we are able to show that p of m plus 1, this statement is also a true statement. This is what we were able to show. And by now what we can do, we can generalize the idea by the principle of mathematical induction. We can say that the original statement, which is given by p of n, this is going to be a true statement. This is going to be true for all values of n. That means any n that we pick up, it must belong to the set of natural number. That means the statement p of n is going to be true for any natural number